So let me show you the tutorial sheet if you haven't seen it already. So the tutorial sheet is if you go to week 7, um, this is the tutorial sheet for today. All right. This is the last of the tutorials of the computer tutorials. So this is the very last one. So I will, as usual, I will go through line by line and also do the exercises. There are a number of exercises. I will do them as I go along. And if you have questions, please feel free to use the chat room. Okay. Um, all right. The first thing I'm going to show you how to do is how to simulate the distribution of the sample variance. All right. To do that, I need to go into this. Okay. Let me copy all there are 4 different functions here. I will explain them as I go along what they do. So, but let me copy all of them now and paste them in the R session. To open R, you go into the Start menu. Um, and then you click here, right? Okay, now I'm going to paste all 4 functions here. Okay. Um, right. The first function is called new. Excuse me. Is called NEWF.1. Now, what is it simulates. So it
What?
simulates 500 values
One new sample.
of
Bravo sample.
it simulates 500 values of n minus 1. Excuse me, what am I doing? Of, can you all see what I'm writing or not? Or not? If you can't see, let me know. If you cannot see what I'm writing, please let me know. So can you see what I'm writing? Yeah. Okay, thank you guys. All right. So what this function does is it simulates 500 values of n minus 1 times s squared divided by sigma squared, where s squared is, excuse me, s squared is the sample variance, right? And sigma squared is the population variance, uh, and n is the sample size, right? And if you look at the nodes, if you look at my the videos that I have done, and you will see that this guy here must have a chi-square distribution, right? Okay, with n minus 1 degree of freedom. Um, so let me write it down. From the nodes, you will see that n minus 1 times s squared divided by sigma squared should have a chi-square distribution with n minus 1 degree of freedom. Distribution. Okay, so that's so. This is something I talked about a while ago. If you look at the video that I did on the chi-square distribution, you will see that this guy here must have a chi-square distribution with n minus 1 degree of freedom, right? If you have forgotten that, please go and have a look at it. Right now, what I'm going to show you is that whether what I'm going to show you now is to use this function new f dot one. This is the function which simulates 500 values of this guy here, right? Now I'm going to show you whether the whether this guy here actually has a chi-square distribution or not, right? To do that, I will go through the following commands. Now, what this command does, excuse me, what this command does is that it simulates 500 values of this, right, with n equal to 50, right, n equal to 50. All right, so now if you do a histogram of what we simulated with frequency equal to f, this is what you will see. See, this is the, so what I have drawn here is the histogram of the simulated values of n minus 1 s squared divided by sigma squared with n equal to 50. Right now, I'm going to define a sequence from 15 to 95. Depends on the range of the x-axis. In this case, the x-axis ranges from, so 20 to 80. So let's change this to 20 to 80, say in steps of 1, right? And then I will compute y as the density of the chi-square distribution at x with the degree of freedom equal to 49. The reason it is 49 is because n is 50, right? So n minus 1 is 49. Now, if you do lines x comma y, this is what you see. So what I have shown you here, guys, is that the simulated data, which is the histogram, right, matches up with the density of the chi-square distribution with n minus 1 degree of freedom, as it should, right? I mean, theoretically speaking, the distribution of n minus 1 s squared divided by sigma squared should follow the chi-square distribution with n minus 1 degree of freedom. And now I have illustrated that fact. Using simulation, right? All right. So as you can see, the fitted density and the fitted density of the chi-squared matches up the histogram pretty well, right? As it should, right? Okay. Now there's an exercise here is to repeat the same thing with n equal to 20 and 100. So let me redo this with n equal to 20 and 100. So I just go back to the previous commands, change this to 20, right? And then do a hist command, right? And this is what you get. The histogram is this one, right? And here you see the x-axis ranges from, say, 5 to 45, I guess. So you change, so you define your x to be from 5 to 45, right? And then you define y with the degree of freedom 19, because now your n is 20, so n minus 1 is 19. And then you do the lines command. You see, once again, the density of the chi-square distribution matches up the histogram of the simulated data well when n is 20, right? And next, when n is 100, right? For n is 100, you do the same thing. So you change this to 100, right? Then you do a histogram. Then you do, okay, this is gonna be 99, right? Okay, because n minus 1 is 99. Before that, you need to define x. All right, let's define x to be 60 to 140. All right, so it's gonna be 60 to 140, and then you define 99, and finally you do the lines command, and you see once again that the density of the chi-square with n minus 1 degree of freedom matches up the simulated data well. Okay. All right. So this is an exercise on the sampling distribution of this of the sampling variance. Right. Are you okay so far or no? Hello guys. Use the chat box, guys. Are you okay so far with what I have explained? Before I go ahead. Hmm? Hello guys. Are you there? Hmm? Hello. Okay, thank you. All right. The next thing I'm going to talk about is the sampling distribution of the sample mean and the sample median, which you should look at the tutorial sheet, right? That's what the next section is about, the sampling distribution um, of the sampling distribution of the sample mean and the sample median, right? Now, all right, to do this, I'm going to use the following function. There's a function called new f dot two. What this function does is it computes the sample mean and the sample median, right? For when you for it okay, let me write it down. It computes 500 values of sample mean, right? Okay, of of 500 values of the sample mean of samples of size n simulated from the normal distribution, right? So do you see what I'm saying? It computes 500 values of the mean of samples of size n simulated from the normal distribution, and it also computes the 500 values of the sample median, right, of samples of size n simulated from the normal distribution, right? So basically what you're doing is you're simulating 500 samples of size n from the normal distribution, and for each sample you're computing the sample mean and the sample median, right? You follow what I'm saying, right? So now, if it's not, please let me know, right? You're simulating 500 samples of size n, each of size n simulated from the normal distribution, and then for each of those samples, you are computing the sample mean and the sample median. Right, now just let me, to illustrate this, for example, you should type new f dot 2 with n equal to, say, 30, right? And let's call this res2. Res2 will have two columns, all right? The first column, let me show you. The first column, x bar, is the values uh, are the values of the sample mean, and the second column, which is called MED, are the values of the sample median, right? Okay, so there are two columns of numbers, and each column is of length 100, of length 500, right? Because as I said earlier, we are simulating 500 samples, each of size n. And for each of the samples, we are computing the sample mean and the sample median, right? And these are the values, right? Now, for example, you should say summary of res2 x bar, right? This is what you get. So what you get is the summary statistics of the sample mean of the 500 sample mean values. N equal to 30. N equal to 30 means, Vincent, that you are simulating. Let me explain that to you again. Now, when I say n equal to 30 here, what I meant is that you are simulating 500 samples, each of size 30, Vincent, right? And for each of the 500 sample, you are computing the mean and the median, and the first column, this column here, gives the 500 values of the mean, and the second column, which is this one, gives the 500 values of the median. So n is the it's the size of the sample that you're simulating. I mean, whatever n is, you are simulating 500 samples, each of size n. So in this case, n is 30, so you are simulating 500 samples, each of size 30, right? Okay, is that clear, Vincent? Are you guys okay with that? All right. So n is the size of the sample that you are simulating from the normal distribution, and 500 is how many samples you are simulating. 500 is always fixed. Is how many such samples you are simulating. That is 500, right? All right. So this is the summary statistics of the 500 values for the sample mean, and this is the summary statistics for the 500 values for the sample median, right? Okay. All right, guys. Any questions, please, please feel free, right? Now, in this case, I took n to be 30. Now, you can also do the same thing with other values. For example, if you take n to be 100, right? Then in this case, what you're doing is you're simulating what? You're simulating 500 samples, each of size 100, right? So you have 500 samples, each of size 100 from the normal distribution. And then you're, for each of the 500 samples, you're computing the mean and the median, right? And if you say this, what you are doing, these are the summary statistics of the median for the 500 samples. And this is the summary statistics of the mean for the 500 samples. Okay, guys, so as you can see, the mean is pretty close to 0, yeah, and the same thing here is also close to 0 here too, right? Yeah. Now you can change, all right, you can change this to 200. If you change this to 200, what's happening here is that, guys, that you're simulating 500 samples, each of size 200. And for each of the, yeah. Remember, each of samples is of size, each of the 500 samples is of size 200. So you're computing the mean and the median for each of the 500 samples, right? Okay, and if you, what these values here are the summary statistics for the 500 sample median values, and these are the summary statistics for the 500 sample median values. Okay. All right. Are you following me or not? I mean, don't hesitate. If you're not following me, please don't hesitate to use the chat room. Okay. Are you guys okay? Hello. All right, thank you. All right, the next thing. So as you can see, as the value of n increases, right, the mean is getting closer and closer to zero, right? As you can see, the mean the mean of the 500 values for the sample mean are 0.006. Here it is 0.004, and the one above is 0.008. So it's getting closer and closer to zero, right? Now you can also do the histograms if you like. You can also do the histograms for the like if you want to know the histogram for the this is the histogram for the sample mean, right? For the sample mean for the 500 samples, the histogram looks like this, right? And the sample median, for the 500 samples, the histograms looks like this. So they are more or less symmetric in both cases, right? Okay, right. Now one property I mentioned some time ago, I don't know whether you remember, this property or not, is the following. Now, if you have data, say x1 to xn from a normal distribution with parameters mu and sigma squared, right? Then the following result is true. X bar is the sample mean, is normally distributed with parameters mu and sigma squared divided by n. Do you guys remember this property? This is a property I talked about some time ago. When I think it's in the video. If you look at the video on the normal distribution, you will see this property that if you have, for a random sample of size n, the sample mean x bar is normally distributed with these parameters mu and sigma squared by n. Now I'm going to illustrate this property using the simulated data, right? Okay, now the first thing I'm going to do is I'm going to do a histogram of this. So you see what I have done here is the histogram of the simulated data for the x bar values, right? Now on top of this, I'm going to draw on top of this the density of this distribution, right? So the first thing I need to do, all right, before that, let me plot this in the frequency scale. I want the frequency to be false, right? So you should say FREQ equal to F for false, right? All right, now, then what I need to do is I need to define the X values as a sequence from minus 0.3 to say plus 0.3. So say minus 0.3 to 0.3 in steps of say 0.01. Then I need to define the Y values as the density of the normal distribution at X with the mean equal to 0, right? And the standard deviation equal to sigma squared by n. Sigma squared is taken to be 1, right? Okay, so it's going to be 1 divided by n. N in this case is 100. Well, n in this case is 200, right? So it's going to be 1 divided by the square root of 200. Right? Do you understand why this is the case? Because according to this formula, guys, the mean should be mu. Mu, or in our case, mu is 0. and the variance should be sigma squared by n. Sigma is 1 in our case, so the variance is 1 divided by n, but n is 200. So the variance is 1 divided by 200. So the standard deviation should be 1 divided by the square root of 200, right? Okay. Now, finally, you use the command lines. Hopefully, you see what you see here, that the density of the normal distribution with these parameters, mu and sigma squared by n, matches up the histogram of the simulated data as it should, right? Okay. All right. So this is just an illustration of the theoretical result. I mean, a practical illustration of the theoretical result that I mentioned earlier in the course, right? Okay. All right. I mean, you can repeat this exercise for other values of n. For example, if you want to repeat for 100, if you want to repeat this for 100, you need to first, right? Let me show you how to do it. If you want to repeat it for, you take it n to be 100, right? And then you do a histogram of this, and you see this is the histogram, right? And then you define x to be -3 to +3, and then you define your y to be d norm at, now in this case, this should be square root of 100, right? And finally, you use the lines command, and this is what you see. Once again, you see that the density of the normal matches up the histogram of the simulated data as it should, right? All right. Any questions on this, guys, so far? So this is the second part of the, so what I have done so far is the second part of the tutorial sheet. Before I go to the next part is on the sample, the distribution of the sample mean, median, and variance of Poisson. Do you have questions, guys, before I do the next part? Hello, guys, talk to me, please. Hello. Or are you lost, guys, or what? Please let me know if you are you guys okay or what? Hmm? Yeah, XI did have a standard normal. Yeah, Louisa, you're right. Yeah. I mean, when we simulated, like if you look at the function nu f dot 2, this, we are assuming that the mu is 0 and the standard deviation is 1. Yeah, so we were assuming that mu is 0 and sigma is 1. So which is the standard normal distribution, right? All right, let's go to the next section, the section number 3, which is simulating distributions of sample mean, median, and variance of the Poisson. So the function that corresponds to this section is this one. This is the function. So what we are doing here in this section, guys, is we are simulating from a Poisson distribution with lambda is 10. So this function does 3 things. It simulates 500 values of the sample mean of samples of size n from Poisson with parameter 10. And it also computes, let me repeat this, 500 values of the sample median of samples of size n from Poisson. And finally, it also computes 500 values of the sample variance. So it does 3 things, guys, 3 things. So it computes 500 values of the sample mean of samples of size n from a Poisson distribution with lambda 10. and sample median also, and also sample variance. So there are three things it computes: the sample mean, the sample median, and the sample variance, right? Now, to execute this function, you use the same command as before. So you say new f dot 3, say n equal to, say, for example, 30, right? And if you call it, say, res3, and if you type res3, this is what you will get. You will see there are three columns of data. The first column here gives the values of the sample mean. The second column gives the values of the sample median, and the third column gives the values of the sample variance. All right. So if you want to compare them, I mean, if you want to compare them, you can do, like, for example, you can do histograms, or you can do I mean, if you want, you can do like box plot. So suppose one way to compare this data is just do a box plot of res3, and this is what you will get. See, um, so there are three boxes. The first box plot corresponds to the sample means, and the second box plot, I can't hear you. Oh, can you hear me, guys, or not? What happened? Can everybody hear me or not? Hello? Is there someone who has problems hearing me? Okay, thank you, guys. All right, there, as you can see, there are three box plots. The first box plot is for the sample mean, the second is for the sample median, and the third is for the sample variance. As you can see, issue the one that has the smallest variability is the sample mean. The one has the largest variability is the sample variance, and so on. All right, and now so the sample median looks pretty odd compared to the other two box plot, because the sample median can only take values that are integer or half integer. Remember, the sample median is defined as the middle value, right? Or the middle value when you arrange the data from the smallest to the largest. The sample median can only take integer or half integer values. Half integer, if the number of data is even, right? If the number of data is even, then it will be a half integer, right? Otherwise, it will be, if the number of data is odd, then it will be an integer, right? Okay. Okay, so this is for n equal to, let me see what this for n equal to 30. Now, if you change this to n equal to 100, right, and then do a box plot, this is what you will get. Again, the story is the same, right? The sample median has the smallest variability for the reason that I just explained, because the sample median can only take values that are actually in the data, right? Where that is not the same with sample variance or sample mean, right? Because of the way this median is defined, that is, it has to be the middle point data, the middle data. It can only take values that are actually in the data. So that's why the variability is smallest. The variability is smallest for the sample median, and second smallest for the sample mean, and largest for the sample variance. Now, if you change this to, say, 200 and do a box plot, this is what is similar again, right? Again, the variability is smallest for the sample median values, second smallest for the sample mean values, and largest for the sample variance. Right. Okay, guys, are you okay so far or not? I mean, is this clear? Like how? I mean, basically, just to recap what I said. This function here, this. Okay, let me new f dot 3. This function, basically what this does is it computes three things. It computes the sample mean, the sample median, and the sample variance for 500 samples of size n, each simulated from a Poisson with parameter 10, right? Okay. All right. The final section of the tutorial sheet is about binomial. It's about comparing, about finding the sampling distribution of the proportion simulated from a binomial, right? So the function that is relevant for this is this. This is the relevant function, right? So what this does, this computes the proportion. This computes the proportion of um, data, right? The sample proportion. Uh, let me write it down. Computes. Right, so this is what it does. It computes the sample proportions for 500 samples simulated from a binomial distribution with parameter n and p, right? Okay, so to do this is the question here is to run this function. So I'm going to run it. I'm going to call this res4 new f dot p n equal to 100. Let's take n to be 100. Let's take p to be 0.6. Right, this is what you get. Now, if you look at the data, this is the data that we just simulated, right? There are 500 values of sample proportion. Okay, now I'm gonna do a histogram of the data. So if you do a histogram of res4 with frequency equal to f, this is what you will see. Right, this is what you will see. Right now, it looks more or less like a normal distribution. I don't know whether you remember. I did this some time ago. That when you have this is a result I mentioned in the class in one of the videos, that the sample proportion is approximately normally distributed with parameter p, the mean p, and variance equal to the sample proportion is, this is a result I actually proved this result. If you look at the video on the binomial distribution, you will see a proof of this, that sample proportion is approximately normal with mean equal to p and the variance equal to p times 1 minus p divided by n. All right. Okay. All right. Now I'm going to illustrate this result. To illustrate this, okay, let me go back to the histogram. Let me define the x values to range from minus 0.45 to 0.75. So I'm going to define x as a sequence from 0.45 to 0.75 in steps of this, right? And now I'm going to define y as the density of the normal at x, right, with the mean equal to p. We took, remember, p to be 0.6, and the variance, sorry, standard deviation is equal to the square root of p times 1 minus p divided by n, which is 0.6 times 1 minus 0.6. N was chosen to be 100, all right? Oh, close bracket, close bracket. And finally, you do the lines command x comma y. Oh, sorry, what did I do? Sorry, lines command x comma y. And this is what you see. See, so what this is another illustration of the theoretical approximation. This time we are approximating the histogram of the sample proportion by a normal distribution with parameters p, and 1 minus p is the mean, and the variance is p times 1 minus p divided by n. All right, so as you can see, it's a pretty good approximation, right? So because the density that I plotted matches up the histogram pretty well, all right? So this is for n equal to 100. You can do the same thing for other values of n. So suppose you want to repeat this for n equal to say 200, right? So you put n equal to 200 here, and then you do a histogram of the data, and it looks something like this, right? So it ranges from say 0.4 to 0.75 or 0.45. Yeah, so you can change you can choose your x to be the same, and you can your y will be the density at the normal with mean equal to 0.6, and the variance this will change to 200, right? So finally use the variance command. Hello guys, no. Hello. Hello, can you hear me? You can hear me now, can you? Okay, okay, thank you guys. So I apologize for not I don't know what the problem was, but I just finished working through the tutorial sheet. I don't know. Did you guys follow me in the tutorial sheet? I mean, did you guys follow everything I did in the tutorial or not? Okay, let me go back to the tutorial sheet just one more time. So this is what I did in the tutorial sheet. I mean, I finished all the exercises in the tutorial sheet. Did you guys follow me or not? All right, that's great, guys. That's great. So I think I kind of finished early today. Maybe I went too fast too. I don't know. If I went too fast, please let me know. I mean, I'm prepared to go back and go go over it again. Um, all right. I mean, one announcement is that this week is the last week before the Easter break. But please don't forget to submit your quiz number 6, which is due on Thursday, as you know, by 10 a.m. All right, so please make sure that you do submit. And if you need any help with quiz 6, please contact me 24/7. All right, all right, guys. So have a good evening, have a good afternoon or good evening, uh, wherever you are, and I will talk to you soon. And any questions, as I said, whether it's to do with quiz 6 or anything, just please feel free to contact me. Okay, you can email me or Skype me or Zoom me, or you can call me at home. My phone number is 01612732941. All right. All right, guys. I'll talk to you shortly. So have a good break. Have a good Easter break. Hello guys, how are you? You guys okay? Are you guys in China or Manchester? Uh, Oh, you are in Manchester. Oh, good to know that. Are you doing something for the Easter break? Because this is the last week before the Easter. Good evening, guys. All right, welcome to the tutorial. So this is the week 7 tutorial, guys. Um, um, so the stuff I'm going to cover today is, if you look at the week 7 tutorial sheet, you will see. So this is the tutorial sheet for today, right? It's on simulation. So I will go through the tutorial sheet line by line and also do the exercises. Right? There are a couple few exercises that we need to do, right? Um, okay. So let me start with page two of the tutorial sheet. Right. Before I do that, let me there are okay, excuse me. There are four functions in R that I need to copy and paste. So let me copy all these four functions that I will need uh, for the tutorial. Okay, and then I open R. To open R, you go into the Start menu, um, and then excuse me, what am I doing? You go into the Start menu, and then you go down the menu and choose R, choose the 64 version, and then you paste the R functions, right? Um, okay, guys. Now the first thing I'm going to talk about is this function called new f.1. Right, what this function does is the following. It computes values of this for 500 for right. That's what it does. Excuse me. I don't know if you can read this here. So what it does is that it computes the values of n minus 1 times s squared. S squared is the sample variance, sigma squared is the population variance, n is the sample size. So it computes the values of that for 500 samples, each of size n, from the standard normal distribution, which is n01. Okay. Okay. So let me just repeat what I just said about. So s squared is the sample variance, yeah, and sigma squared is the population variance, which in this case is 1, right? And n is the sample size, right? So this function here, which is new f.1, it computes 500 values of this for 500 samples of size n simulated from n01. Okay. Now I don't know whether you remember. Uh, you, you should remember that one of the things I taught you in the class is that this guy should have the if you look at the video I did on the chi-square distribution, one of the results I mentioned in that video is this, that is n minus 1 s squared divided by sigma squared should have the chi-square distribution with n minus 1 degree of freedom. All right. Okay. Do you remember that result or not? I mean, maybe some of you forgot. If you have, then please go back and look at the video. If you look at the video on chi-square, you will see this is one of the results. This is one of the results I mentioned in that video, guys. Right now, what I'm going to show you is I'm going to show you using simulation how how to illustrate this result, right? So to do that, I'm going to first simulate 500 numbers with n equal to 50. N equal to 50. So if you type res1 now, you will see I have 500 numbers, right? Similar 500 values of this, right? Of 500 values of this simulated with n equal to 50, right? So in other words, 500 values of this, uh, each computed out of 500 samples of size 50 um, from N01, right? Okay, the next thing I'm going to do is I'm going to do a histogram of this with frequency equal to f. So this is the histogram of the simulated data. Hopefully you can see it. Yeah, you can see this now, right? And next thing is I'm gonna plot on top of this histogram the density of the chi-square distribution with n minus 1 degree of freedom. To do that, first I need to define the x-axis. So let's say 25 to 85. So let's take the x-axis from 25 to 85 in steps of 1, and y as the density of chi squared at x with the degree of freedom equal to 49. Is 49 because n is 50, so n minus 1 is 49. And then finally you use the command lines x comma 1, and this is what you will get. You see here, what you see is the justification of the theoretical result, that the simulated data, the data is simulated values of n minus 1 s squared divided by sigma squared should follow the chi-square distribution with n minus 1. And the density, which is the curve, is the density of the chi-squared, with n minus 1, in this case, 50 minus 1, which is 49. All right, so as you can see, guys, the density matches up the histogram pretty well. And that's what you will expect because of the theoretical result that says that that's the statistics n minus 1 is squared divided by sigma squared should follow the chi-squared with n minus 1 degree of freedom. All right, so that's what you see. So in this case, I've taken n to be 50, but you can do the same thing with other values for n. So suppose I choose n to be 20, right? Then your histogram is this. So as you can see, the histogram goes from 5 to 40. So you define your x-axis to go from 5 to 40 in steps of 1, right? And then you define your y. In this case, since n is 20, n minus 1 is 19, right? And finally, you use the lines command. And this is what you see. Once again, the fitted density, which is the density of the chi-squared with n minus 1, is a good fit to the simulated data, or the simulated histogram, right, as it should. All right, and finally, let me choose n to be 100. Right, in this case, I'm going to choose n to be 100. Then I do a histogram of the simulated data, which is this. You can see it. So it goes from 60 to 180. So I choose the x-axis to go from 60 to 180 in steps of 1. And then you define the y. In this case, your degree of freedom is 99 because n is 100. So n minus 1 is 99. Okay. And finally, you use the lines command. And this is, you see, once again, as the theoretical result says, the fitted PDF must be a good match to the simulated histogram. All right, guys. So is this clear or not? So this is the first section of the tutorial sheet, which is about the sampling distribution of the sample variance. Are you guys okay with this? Any questions before I go to the next part? Hello, guys. Talk to me, please. Are you all of you okay? Good. All right. So the next section I'm going to talk about is the sampling distribution of the sample mean and the sample median. So for that I'm going to use the next function. There's a function called new f dot 2, right? And what this function does is the following. It computes 500 values of well, let me put it like this. Computes values of the sample mean for 500 samples, right? Each with each of size n simulated from n01, right? Okay. And it also computes the sample median. So there are two things it does. It computes the sample mean and the sample median for 500 samples, each of size n, simulated from the standard normal, right? Now let me illustrate this, right? So if you say res2 equal to new f dot 2 with n equal to say 30, now if you type res2, you will see this. You will see this, right? Sample mean for the 500 samples. Can you hear me, guys? I think there's a problem with the camera. Oh man, can you hear me, guys? Okay, thank you. All right, I was just checking my audio. Sometimes the audio doesn't work. So if you can't hear me, please let me know. Okay, I think I had a problem with my audio last time. All right, the first column is the values of the sample mean. The second column are the values of the sample median, right? There are 500 of them in each column, okay? All right, guys. Next, you should type box plot. You should do a box plot. I will show you. You should do a box plot of res2. This is what you will see. You see, both of them are pretty symmetric, as you would expect, right? And there's little difference between the two, although you can say that the sample mean has a smaller variability compared to the sample median, right? It's only slightly smaller compared to the sample median, right? Okay. Now let me run this with other values of n. Now here I took n to be 30. Let me take it to be say 100, right? And then do a box plot. And again, this same story, right? They are very similar to each other. And once again, the values of sample mean have smaller variability compared to the values of sample median, right? And finally, let me take it to be n to be say 200. In this case, once again, it's the same story, okay? Right. All right. Now one thing I want to show you is, I don't know whether you remember that if this is something I talked about in the class. Suppose suppose you have x1 to xn, which are IID from a normal with mean mu and variance sigma squared. Right? The sample mean is also normal with parameters. Do you remember this result? This is a result I talked about in the class some time ago. I think it was in the video on normal distribution. So if you don't remember this result, and if you go back to the video on the normal, you will see this result, that the sample mean of a sample from a normal distribution is also normal with parameters mean equal to mu, the variance equal to sigma squared by n. Now what I'm gonna illustrate is the if you look at these, sorry, x bar, these are the excuse me, these are the values of the sample mean, right? So according to the theory, these values must follow a normal distribution with mean equal to mu and variance equal to sigma squared by n, right? Okay, that's according to the theory, right? Now let me check whether that is actually true or not, right? To check that, I'm gonna do a histogram. So let me do a histogram of this, right? So this is the histogram of the simulated values for the sample mean. Now, all right, let me do it in frequency equal to f, equal to f. So this is what you get. You see the x-axis goes from minus 0.3 to say 0.3. So let me define the x-axis is as a sequence from minus 0.3 to plus 0.3 in steps of this, and y is the density of the normal at x with the mean equal to 0, because our mu is 0, and the standard deviation equal to 1 divided by, if you go back to this, I took n to be 200, right? And if n is 200, then sigma squared divided by n will be 1 over 200, because our sigma is 1 and mu is 0. So this is 1 over 200 is the variance. So the standard deviation, excuse me. So the standard deviation will be 1 divided by the square root of 200, right? Okay. And finally, I would use the lines command x comma y. And you see here that what you see here is a illustration of the theoretical result. That is the histogram of the sample means, right? Follow a normal distribution with mean equal to mu and the variance equal to sigma squared by n. I mean, that is supported by this picture, right? So in this case, I chose n to be 200. Now let me redo this with n equal to 100. Right, let me redo this with n equal to 100. So let me go back and change this to 100, right? And then I'll do a histogram like this, and then I define the x values to be this, and define the y to be, now I change this to 100, right? Because this, remember, sigma squared divided by you use the lines command. This is what you get. All right, as you can see, this is a pretty good picture. As you can see, we have the simulated histogram fitted pretty well by the density of the normal with mean 0 and variance 1 over 100. Please let me know. I'm just Please let me know if you can't hear me. Okay, can you guys hear me, please? Hello. Okay, thank you. Okay, thank you, guys. All right. So so this is so did you follow what I just explained, guys? So are you? I mean, I just explained to you the fact that the sample mean of a sample simulated from a normal should also have a normal distribution with mean equal to mu, and I really don't know why, George. I don't know what the problem with my audio is. I will try to check it out, but I mean, let me check just a minute. I don't know why my videos, sorry, my audio sometimes gives me trouble. Hello, hello. Okay. Is it better now or not? Hello, guys. I hope. Okay, thank you, thank you. I don't know why this problem arises. All right. Okay. So did you follow what I just said, guys? That is, I mean, the illustration that I just made is to illustrate the fact that the sample median of a sample from a normal, right? Sorry, the sample mean of a sample from a normal distribution follows also a normal distribution with mean equal to mu and variance equal to sigma squared divided by n. All right. I hope you guys you followed that. Okay. The next thing I'm gonna talk about. The next thing I'm gonna talk about is how is the sampling distribution of the sample mean, median, and variance from a Poisson distribution. All right. For that, I'm gonna use the following function. Right. This is the function. Oh, it's cracking again. Oh man, I don't know what the problem is. Let me check. Let me check again. Um, test make testing 1 2 3 1 2 3. Okay, hopefully better now. I don't know. All right. Okay. What this function does is it does three things. It does this function called new f dot 3. It does three things. It computes 500 values of the sample mean of, okay, I mean, it computes values of the sample mean of 500 samples, each of size n, simulated from Poisson with parameter lambda equal to 10, right? And it also computes the sample median for the same, and it also computes the sample variance for the same. So you can see it does three things. It computes the sample mean, it computes the sample median and the sample variance for 500 samples, each of size n, simulated from a Poisson distribution with lambda equal to 10, right? So now let me show you how to illustrate this, right? So suppose suppose I say res3 equal to say new f dot 3 with say n equal to say 30, right? Now, if you type res3, you will. This is the data that you will get, right? So the first column are the 500. Excuse me. The first column are the 500 values of the sample mean. The second column are the 500 values for the sample median, and the third column are the 500 values for the sample variance, right? Okay, now if you type box plot, this is what you will get. There are three box plots, right? The first one is for the sample mean, the second is for the sample median, the third is for the sample variance. So as you can see, the variability is the largest for the third one, and the first one, the second one are not too different, right? The second one is a little bit odd because as you saw from the data, as you saw from the simulated data, the sample median, remember the sample median is defined as the middle value in the data when you arrange it from the smallest to the largest, right? So therefore, the sample median has to be equal to one of the data values, right? Right, has to be. I mean, remember, Poisson can only take integer values like 0, 1, 2, 3, etc. So the sample median has to be equal to an integer value or half an integer value, right? Okay, so that's why you see in the middle column, excuse me, with somebody, in this case, n is 30, Jack. N is 30 in this case, Jack. You remember what I mean? Right? It can only be integer or half integer, right? Because of the way the sample median is defined. That's why this box here, the middle box that you see here is pretty odd because it can only take, the variability is so limited because of the way the sample median is defined, right? Now, if you suppose n, you take n to be say 100, right? And then you do a box plot of it. Now you see this. It's a similar story, right? Similar story here. Again, the variability is largest when for the third box, but the variability of the first two boxes are similar, right? And finally, suppose you choose n to be 200 and then do a box plot. This is what you see here. Once again, the second box is pretty weird because for the reason that I just explained, that the sample median, the values of sample median can only be integer or non-integers. Therefore, the variability of the values for sample median can be very, very small uh, compared to the other two boxes, right? Right. Okay. All right, guys. Any questions on this? Hello, guys. Talk to me. Are you okay with this, guys, or not? Um, Everything okay? So what is the what? Yeah, everything okay. So okay, thank you. Um, all right, okay. All right. So let me go to the next section. The next section of the tutorial sheet, which is about the sampling distribution of sampling proportion. So the function that corresponds to that section is called new f dot 4, right? So what this function does is the following. Let me write it down. It computes. It computes. It computes 500 values of the sample proportion for data simulated from a binomial distribution with n parameters n and p. Right? Okay. Now I'm going to show you how to. I don't know whether you remember that. I don't know whether you guys remember that one of the results that I mentioned in the video on binomial distribution is the following: that the sample. Okay, let me write this. The sample proportion is approximately normal with parameters p and mean equal to p and variance equal to this. Do you remember this result? This is a result. Actually, I proved this result. This uh, follows by the central limit theorem. I mean, if you don't remember this result, please look at the video on the binomial distribution, and you will see that I gave a proof of this, that the sample proportion is approximately normal with the mean equal to p and the variance equal to p times 1 minus p divided by n. Now I'm going to illustrate. This is a theoretical result, so I'm going to illustrate this result using simulation, right? So the first thing I'm going to do is I'm going to use the new function dot for with n equal to say 100, and say let's choose p to be say 0.6, right? So p, this should be p. Okay. If you have a question, please let me know, all right? And then I'll do a histogram of this, right? And this is what you will get, right? The x-axis goes from point 0.45 to 0.75. So you choose x to go from sequence 0.45 to 0.75 in steps of this, right? And you choose y. You choose y as the density of the normal distribution at x with the mean equal to p. Remember, p is 0.6 now, and the standard deviation equal to the square root of p times 1 minus p divided by n. So it's going to be the square root of p is 0.6, 1 minus p is 1 minus 0.6 divided by n. N is 100. Okay. All right. Now finally, you use the lines command x comma y. Oh, it doesn't work here. Do you see why it doesn't work? Because I made a mistake. I did this deliberately because I wanted you to check. Do you guys see why it didn't work here? The reason, because I plotted the y-axis in the frequency scale. It should be on the density scale, not on the frequency scale, right? All right, so let me redo this again. So I go to this, plot this in the density scale, which is this one, right? Then do the x, then do the y. Sorry, I have already done this. Then finally use the lines command. Now you see it does work, right? The reason it didn't work earlier because I plotted the histogram in the frequency scale, which is not correct. It should always be in the density scale, but especially when you want to compare the histogram with the density of a distribution, you should have it in the density scale, right? Anyway, so you see now that you see now that the density of the normal is a good approximation for the simulated histogram. They look pretty close to each other, as you can see, right? So it kind of illustrates the theoretical result, which is this one. This is the theoretical result which I taught you earlier in this course, right? Okay, so all right, now let's try this with the different value for n, right? So let's go back and change, say, n to, let me just a minute. Let me change n to, say, 200, right? Change this to 200. Then do a histogram with the frequency equal to f. This is what you get, right? So the x-axis ranges from 0.5 to 0.75. So you change x to go from 0.5 to this. And the y, you choose y to be the density of the normal with mean 0.6. The variance, okay, now you should divide by 200, not 100. So change this to 200. And finally, use the lines command. And once again, you see it's a good match. The density of the normal is a good match to the simulated histogram, right? Are you guys okay? Hello, guys. Any questions so far? Are you guys okay or what? Talk to me, guys, please. Did you, what do you, So the purpose of this, the purpose of the last thing I did, right, it was to show you that, to illustrate the theoretical result that the sample proportion follows the normal distribution with these parameters. So each of these things I did was to illustrate this. Now you can also change the value for p. So suppose, right, let's do this. Suppose you simulate with p equal to, say, 0.1, right? Then you should do the histogram. This is what you see. So the histogram goes from 0.04 to 0.17. So you choose your x-axis to go from 0.04 to 0.17. And you choose your y-axis. So your y-axis is going to be the density of the normal with the p is now 0.1. Right, change this to 0.1, right? And then you use the lines command. You see, once again, the density of the normal is a good fit for the simulated histogram. I mean, that's the theoretical result. So it should be the practical. I mean, the simulated result should match up with the theoretical result, right? And that's what we see. That's what we see here. Okay. All right, guys. And you can also change, once again, if you want to change n to 100, you can do that too. Right, let's change n to 100 now, p equal to 0.1. Then you do a histogram and it looks like this, right? So p goes from, say, 0.01 to, say, 0.20. So you change x 0.01 to 0.20 like this, and your y, your n is going to be 100 this time, so you change n to 100, and this is what you get. You see one more time that the density of the normal is a good fit to the simulated histogram. All right, guys, so this completes the tutorial sheet for today. I know I kind of finished early today because it's a short one today. It's a short tutorial sheet today. You guys have any questions on stuff I did today? Please feel free. I mean, don't be shy. Any questions on stuff I did today, guys? Please let me know. Talk to me, guys, please. No, no questions. No. All right. Okay. So as you know, this week is the last week before the Easter break. So I wish you a very happy Easter break. And but you can, I mean, I'll be in Manchester throughout the Easter break. So any questions you guys have, please feel free to contact me 24/7 by email, Skype, Zoom, or phone. My phone number, I said this many times, is 0161 273 2941. Right, you can call me 24/7. And you can, I'm also happy to meet you in Manchester. If you are around in Manchester, I can meet you anywhere, and go through problems with you. And yeah, and by the way, the quiz number 6 is due, as you know, it's due this Thursday, 10 a.m. So please submit. Please remember to submit it if you haven't already done it. Please submit quiz 6 before 10 a.m. on Thursday this week. I mean, I have done 20 examples for quiz. I mean, 20 worked examples for quiz 6. So you shouldn't have. I know it's not easy. None of the quizzes are easy. I mean, they are not. I mean, if I make them all easy, then it's easy to get 100%. I mean, but if you need help with any of the quizzes, including quiz 6, please contact me. Right? Any help you need with the quizzes, just feel free to uh, phone me or email me or whatever. Right? I'm happy to help. Okay. All right. Any questions you guys have now? Hello, guys. No questions. All right. So um, so have a good evening, guys. So I'll talk to you. I will talk to you soon. Whenever, I mean, you call me or whenever, I will talk to you. But have a good evening and have a happy Easter break. Right. Um, okay.